How can we determine if a limit exists?
If it exists approaching from the right and the left, and that's the same value.
Yep, then the limit there exists, correct? So we can do it with just equations, but we're going to do a sketch anyways, because sketching, I was like, oh, we don't need to do the sketches, which I've done in the past, and then I watched the sketches after, and I was like, oh, we should have done the sketches. Yes, we should. So we're going to go do them. I know, I'm using the line feature.
She's using the line. No, her hand is just that steady. Line.
You know, it's fine. I got this. Okay. So we can write a piecewise function as two pieces. So I'm going to draw the blue, this piece in blue. So I have 3x plus 1 if x is less than 2. So I'm going to start at the 2, correct? With a what dot? Open. So when I plug 2 in, I get 3 times 2, which is 6, plus 1, which is 7. So I'm at 2 and 7. 1, 2, 3, 4, 5, 6, 7. I have an open dot. Then I need to work my way backwards. So I could plug in 1. 3 times 1 is 3 plus 1 is 4. Thank you. Oh my gosh. Nice. And then we'd have 0 and 1. And we could use our slope if we wanted to. So instead of up 3 over 1, we could go down 3 left 1. And that would be on the left. So from that graph, we can say, okay, the limit as x approaches 2 from the left of f of x equals what? 7. We'll do the algebraic process after. Okay, then I'm going to do, so I get f of x equals 2x x minus 1 if x is greater than or equal to 2. Now I'm actually going to, so you'd have your x-intercepts at 0 and 1 on this one. But we literally, like if you look at this, your x-intercepts are at 0 and 1, correct? It's a concave up parabola, yeah? This would be the same as saying 2x squared minus 2x. Like it's a concave up parabola. And this is in factored form, so our x-intercepts would be at 0 and 1. However, this starts at 2, right? So all I literally have is an arm coming off of this graph. If you visualize it, it's going down, making a minimum, going through 0, making a minimum, going through 1, and then an arm, right? So we just have an arm. So some people are like, I have to find the minimum. The minimum doesn't exist on this graph because we don't have that piece. We have 0 to 1, then just the arm. Okay? So we're going to start at 2 first. So when we fill a 2 in, we get 2 times 2, which is 4 times 2 minus 1, which is
1.
So 2 times 1 is?
Oh, wait. Oh,
2 times 1.
2 times 1 is
2 times 2 is 4, and then 2 minus 1 is 1, and then 4 times 1 is 4. Good answer. Cool. Great. So do we have a closed dot or an open dot?
Closed.
And we have closed because it's equal. All right. Good talk. Let's fill in a 3. 2 times 3 is 6. 3 minus 1 is 2.
12.
6 times 2 is 12.
it don't fit. Or just add, you can't all just add more to the graph.
Yeah, you can. It's your graph.
Not if you don't have space.
Well, then make space.
Sounds like an ish you, not an ish me. See?
I've heard that line.
Yeah, my daughter hates it, so I continue to say it. All right. Proof. Carries on. Make sure you have arrows because the arrow shows that the graph continues, correct? Yeah. So from this graph, we can say the limit as x approaches 2 from the right of f of x equals 4. So we can say that the limit as x approaches 2 of f of x, what? Now we can actually show it algebraically as well. Because these are polynomials, the value at them is what they will approach, right? Remember we talked about that? If it's a polynomial or a continuous function, the limit as you approach it actually is the same as the limit at that value. It's continuous, limit from the left, limit from the right, limit at that value, all is the same, correct? So because both of these are polynomials, one is linear and one's quadratic, I could actually plug 2 into here and I'm going to get 7 and get the limit that way from the left. And then from the right, I can fill 2 into here and I'm going to get 4, and then I get my limit from the right. Like I can do it algebraically because I know it's continuous. If it's continuous, the left, the right, and at that value will be the same. And every continuous function will have that happen. Polynomials are always continuous, right? There's no spots for it. Now, these are not continuous because it's a piecewise function. Their separate pieces are continuous, right? But if we sketch it, we can see that this one's approaching 7, this one's approaching 4. They do not approach the same thing, and they're therefore not continuous, right? Now, what if I asked you this? What if I asked you for f of 2? Which equation would you plug it into?
The second one,
Because it has
a closed dot.
a closed dot, has an equal sign as well, right? So what if they both didn't have equal signs? What would f of 2 be? Doesn't exist, right? But this one there is, so I can plug it into this one. So I get 2 times 2, 2 minus 1, the big debacle in question. 4 times 1 is, oh boy. Oh wait, then the next page. All right. Find the power and the limit of a root. So using the limit of product, if the limit as x approaches c of f of x is squared, then I can write them both as multiplied instead of squared. Then I can write them as separate limits. Then I can take the whole limit and put it squared. So whenever I have the limit as this is squared, I can actually delimit the whole thing squared. So that's a rule you can use. For these ones, if you can just plug it in, can you just plug it in? Do you have to do anything fancy? Do you have to show the limit rule? No. It's just showing you why that limit would exist in that way. So for these ones, do I have a problem if I plug the 2 in?
No.
So can I just plug the 2 in? Yeah. When I plug the 2 in, what happens?
You get 32.
True fact. What happens? The limit word. It disappears. So the moment you plug in the value, you substitute in the value for x, the limit goes away. The limit is there to show you what the heck you're substituting in for x. So let's see if this fact is true. So if this is cubed, it's saying that this should equal the limit as x approaches 1 of 2x minus 3 all cubed, if that's a true statement, correct? Let's see if it's true. So I can plug a 1 in right away because it works. So I'm going to go 2 times 1 minus 3 to the 3 equals negative 1 to the 3 equals negative 1. Well, this one I would plug the 1 in, so I'm going to get 2 times 1 minus 3 all to the 3. Negative 1 cubed is negative 1. So it does work. At least for that example. But the theorem up top tells you it works forever. Okay, what about this one? You plug c in for x. So I'm going to get c to the n. Done. Now people will say to me, I don't know if I should plug it in for the x or the n. Well, it says x becomes c. So you're going to put it in for the x, right? And here it says n is a positive integer. So n is actually not a variable. N is like 4 or 8. Okay?
We had a weird situation where it would say, like, as n approaches c, then would we put c in for n?
Yep. Yep. So here it says theorem, limit of a root. If the limit as x approaches c of f of x exists and n is greater than 2 is an integer, then the limit as x approaches c of the square root of, or nth root of f of x equals the nth root of the entire limit. So it's the same thing. When you have an exponent, you could do the whole limit to that exponent. When you have a root, whether it's squared, cubed, fourth root, you can do the whole limit and then take the fourth square cube root of it. So what does that mean? That means I can do it this way, or this should, nope, thanks board. Or this should be the same as the limit as x approaches 4 of x squared plus 11 cube rooted. So we get, I can plug the 4 in, I can get the cube root of 4 squared plus 11, which is the cube root of
47.
27, there we go,
Approximate knowledge.
equals 3. He was joking, podcast. He was looking for humor. He didn't really think that was 47.
Right, Peter?
Right, Peter?
Why?
I didn't check anything.
You just shouted. Okay. So, for this one, we plug the 4 in. We get 4 squared plus 11. And so we get the cube root of 27. And then this one, the same thing. You could raise it all to the 3 halves. Because the 3 halves is just what? The square root of this limit cubed. So it's just putting the 2 rules together, right? But in this case, because there's no problems, I can just plug it in. I can go 8 plus 1 to the 3 halves, which is 9 to the 3 halves. Take the 2, drop it in front. So I get the square root of 9 cubed, which is 3 cubed, which is
96.
27. That's it for today.